So I'm very happy to present our first speaker of this invited session, is Yuval Ronen from Harvard University. He'll talk to us about induced superconductivity in fractional quantum Hall edge. Yuval, the stage is yours. You're mute.
You can hear me well?
Absolutely.
Okay, thanks. And thank you, and for the organizer for inviting me also. Okay, so I'll talk about the induced superconductivity in the fractional quantum Hall effect edge. And basically what we try to do in this work is to combine two many-body effects. One is fractional quantum Hall effect, and the other one is superconductivity in van der Waals materials. And I really had the privilege of working in this work together with Under and Xiang and Jonathan on the experimental front, and with Hassan and Ashkin, which did the theory, and all of this work was done in Amir Yacobi and Philip Kim's lab. Okay, so this is the device that I'm going to talk about, and of course, you know, we'll go into it as we go, where we try to induce superconductivity in the fractional quantum Hall effect. But another experiment we also did, which has a similar nature, is this experiment, which is interference in the quantum Hall effect. And you know, each of these experiments has its own goal, but really the motivation for both of them is to realize quasi-particle, which has a unique exchange statistics. And what is exchange statistics? So I know all of us know, but I'll give one slide about it. So it's basically what happened to the many-body wave function when we interchange two indistinguishable particles. So for example, in 3 dimension, we know we have only bosons and fermions. So for boson, this new wave function, after we interchange the two particles, it's just the initial wave function with a plus sign. And for fermions, it's the initial wave function with a minus sign. But in 2D, we can actually have a new spectrum of particles, okay? And these particles are called anyons. And the simplest anyon is called the abelian anyon. Abelian anyons are when we interchange two particles, we get the initial wave function times time phase e to the I theta. And one place we can find this abelian anyon is, for example, in the fractional quantum Hall effect at a filling of 1/3, okay? Now, a more interesting anyon is the non-abelian anyon, and you see that the initial wave function is already a vector, and this is because non-abelian anyon are living in a degenerate ground state. So we can think about some high degenerate Hilbert space, and this initial wave function, you know, is some vector in this Hilbert space. And basically, when we interchange two of these non-abelian anyon, we move to another place on this Bloch sphere. So there is some rotation, and this is this unitary matrix, which is basically describing, you know, the exchange of these two particles. And another place, again, that we can find this non-abelian, maybe we can find it, is in the 5-half filling in the fractional quantum Hall effect. And people took this idea, of course, of non-abelian and tried to make a prediction of how can we make a topological qubit out of it. And this, as you all know, really started this field of topological quantum computation that, you know, Jenny was alluding to. So there are many ways that people are trying, you know, to create this non-abelian anyon, the intrinsic way, for example, in the fractional quantum Hall effect, but there is also like artificial way of creating this topological superconductor. And in the second experiment that I mentioned, we basically tried to go into the more intrinsic way of probing this state. But today I'll talk about the other scenario, which is basically synthesizing this topological superconductor. So all of these directions started from Fu and Kane in 2008. And basically the ingredients that Fu and Kane draw for us is that we need a pair of helical states. Like, so I'm going to briefly talk about it because Jenny really described it well, which are basically counter-propagating edge state or surface states, which has opposite spin. And we need to proximitize this edge state with an S-wave superconductor. So when we proximitize them, we basically open a gap, we get a new phase, which is called the topological superconductor phase. And at the boundary of this phase, we should have these non-abelian anions, which are sometimes they are called the Majoranas zero mode. And there are many different options one can create. These Majoranas zero mode. You can proximitize superconductor to a 3D or 2D topological insulator, to a 1D semiconductor with spin orbit, or in ferromagnetic atomic chain. But now I want to talk about an alternative platform, and you'll see that it has some interesting twist. So the platform is actually quite simple. You take a two-dimensional electron gas, you put filling factor 1, for example, in the quantum Hall effect, and then you get an edge state which is surrounding the system. Then you can make a trench inside this two-dimensional electron gas, and you fill this trench with a superconductor. Now, if we zoom into this section, and we focus on the middle, basically you can see here two counter-propagating edges, which are proximitized by this superconductor. And these two edge states which are counter-propagating, the difference between Fu and Kane idea and this realization is that these two edges actually have the same spin. Okay, so if you want to proximitize this counter-propagating edge state, what you need some kind of a spin orbit mechanism. And this is what I'll show you when I'll get to the results. Now, what is the advantage of this alternative platform? Okay, so as I said, with these systems, you can basically try to create Majoranas zero mode. And the idea is that one can create a Majorana qubit based on them. And for example, how would this qubit work? Basically, you will initialize it at some state, right? And by doing these braiding operations, you'll basically move in this Bloch sphere, right? That's like the rotation that I showed you before. Now, braiding of Majorana zero mode basically can give you 90-degree rotation. So it means that if you started, on the North Pole, you can only access to, 4 different points on the equator and to the South Pole. So you can only access 6 different points, which means it's not possible to create a universal gate set. You have to have like 45-degree rotation in order to get a universal gate set. So this really means that, if you base, if your quantum computer is based on Majorana qubit, you are limited in terms of topological quantum computation. Now, of course, it's not that we have today, a topological qubit and we are stuck, but it's something, of course, to be aware of. And in theory, this started around, I think, 7 years ago. It started this pursuit for a more richer non-abelian quasi-particle, which are sometimes called parafermions. And using these parafermions or parafermions array, one can create a universal topological quantum computation. And this was summarized in this paper, which is called, Universal Topological Quantum Computation from a superconductor abelian quantum Hall heterostructure. And really, what this paper outlined is that you need to combine fractional quantum Hall effect and superconductivity, and this is what we're trying to do in this work. Now, in the spirit of what I outlined before of Fu and Kane, the idea here is basically to add electron-electron interaction. So you need a pair of helical states, and you need these helical states to have electron-electron interaction, and then you need to proximitize it by an S-wave superconductor. And basically, these two ingredients together are saying, I want to have a fractional helical state, and I want to proximitize it with an S-wave superconductor. Okay. So now, how did we tackle this problem? So the structure that we are using, the middle layer is graphene. Okay, that's the active layer, and there is a bottom and top BN, which are the electric material, and 2 graphite gates, which help us control the density. This is the stack before fabrication, and this is the stack after fabrication. So in purple, you can see basically the van der Waals structure. And in gold, this is just normal contacts from palladium gold edge contacts. And in blue, this is the niobium nitride superconductor. The critical temperature is around 12, 13 at 0 magnetic field, and the critical field is 27 Tesla at 1 Kelvin. So that's very important because you want to see fractional quantum Hall effect and proximitize it with the superconductor. And really the heart of the device is this superconductor finger. And the width of this superconductor finger is around 100 nanometer, and the graphene itself is around 80 nanometer. and there is no graphene under the superconductor. So this superconductor is basically touching the graphene from the side, okay? You can also see here these bridges, which are basically contacting the top graphite, okay, and the bottom graphite at different places. So we made around 15 devices and 5 of them were measured. It takes around 3 to 4 weeks to make a device. Now, really the heart of the device is here, and basically we are bringing this quantum Hall edge into the superconductor. So let's understand for a second, how does current flow between this edge and the superconductor? So for that, just let us remind how does current flow between normal and superconductor. So if we have an electron which impinges on the superconductor and the superconductor is gap, right, the electron cannot come in. So it takes another electron from a negative energy, which is basically reflecting back a Hall, and then it forms a Cooper pair. Okay, and this process is basically called Andreev reflection. Now we can change the left part to quantum Hall edge. And now the same thing applies, right? The electron reaches the superconductor, it impinges on the superconductor and then reflects as a Hall. However, this Hall is reflected again from the superconductor, and this is the formation of the Andreev edge state. Now, in our experiment, we are actually not interested in Andreev edge state physics, but something else. So what we are doing, we are adding another terminal on the other side, another quantum Hall edge, and we are also making the superconductor very narrow compared to the coherence length, okay, or at least comparable. So you need to think that the size of the Cooper pair is around this size, okay? So what can happen now is when this electron impinges on the superconductor, it can take this electron from a negative energy, or it can take an electron from the other side. So that's another microscopic process. And taking this electron from the other side is basically a Hall which is continuing to propagate in the other quantum Hall edge. And this process is called cross-Andreev reflection just because it's across the superconductor. And what we want to look at, at the Fermi level of this transmitted edge, and seeing indeed that we see a negative voltage. A negative voltage will basically tell us that cross-Andreev reflection occurred and the two edges are induced. Okay, so this is what we are interested in. So this is the sample that we measured. We inject current from this contact. We apply a large magnetic field, so we have quantum Hall edge state. So you can think this is, for example, the picture in filling factor 1. You have the edge state which is advancing to the superconductor. The superconductor is grounded. So the Fermi-Dirac distribution of the impinging edge looks something like this, right? This is the chemical potential. And every electron which is above the chemical potential, if only cross-Andreev reflection happens, will take an electron from negative energy, from the transmitted edge. So the Fermi-Dirac distribution of the transmitted edge, if there is 100% of cross-Andreev reflection, it should look something like this, okay? And what we measure in the experiment, we measure this negative voltage. 5 minutes? Okay, I see. So we have, and we measure this negative voltage, okay? So this is this V car, and really the measurement that we are doing is R car, which is V car divided by the impinging current, okay? So this is really the figure of merit. So we cool down the device. This is the RXY and the R car, and let's make a cut at 4 Tesla. So here you can see the RXY, RX6, and R car, and you can see that R car is indeed negative as I explained before. And really, if we want to look at R car, so R car is actually not exactly what we need to look at. If we want to look at R car per edge, we need to divide R car by RXY. And if we do that, we actually see that the probability for cross-Andreev reflection is completely constant between the different integers. And this is surprising because, for example, filling factor 1 is polarized, but filling factor 2 comes with both spins. So that was something interesting to see. Another interesting measurement that we can learn from it is looking at the bias dependence of filling factor 2 compared to filling factor 6. So you can see that the gap for filling factor 2 is much larger than the gap of filling factor 6, which makes sense because the edges are basically farther away from the superconductor, so the induced gap is smaller. And now if we apply a larger magnetic field, right, we can get to fractions, but for fractions there is additional complication. And the complication is now that the charge is actually fractional. So for example, for a 1/3 filling, the charge is E/3. So you can imagine a charge of E/3, right, which comes to the superconductor, and now it wants to tunnel inside. So maybe the straightforward way it can happen is that this E/3 charge will basically wait to another 2 E/3 and then jump into the superconductor as an electron, right? And a hole will be transmitted. And this is what I try, to illustrate here, which basically says that the superconductor absorbs a 2e charge. Another scenario can be that every quasi-particle which comes actually creates cross-under reflection by itself. But that will mean that the superconductor actually absorbs 2e/3, which is something we wouldn't expect, but that was actually theoretically predicted in 2014 by Clark et al. And just intuitively to understand how does it absorb these 2e/3, so the parafermion states are actually absorbing this charge, and this is how you reconcile this problem. Now, experimentally, if we can identify if this scenario is what's happening or this will actually tell us if we have parafermions in our system or actually the bunching occur. So now we just make the cut at 9 Tesla. And again, you see the cuts of Rx6, Rxy, and Rcar. And you can see here the negative for the integer, but you also see the negative for fractions. And that means, you really see cross-under reflection for fractions, and you are able to induce superconductivity on fractional edge. I'll finish in 1 minute. But the temperature dependence of this fractional, you see it becomes negative around 4 Kelvin. And then for integer and 2/3, it becomes a constant. However, for 1/3 and 2/5 is actually becoming more and more negative. And actually, if I add here a point for the dilution, these lines really continue to go down. Now, interestingly enough, temperature dependence can actually distinguish between this bunching of quasi-particle or cross-under reflection of each quasi-particle by itself. So the bunching scenario should actually, the cross-under reflection should go to 0 at 0 temperature, but as under reflection for each quasi-particle, the cross-under reflection should increase. This is indeed, what we see in the experiment. Now, I'm not claiming it's a direct proof, but it suggests that what's happening is really the second scenario. So to summarize, what I showed you is, first of all, superconducting pairing in the fractional quantum Hall effect, evidence for spin orbit when filling factor 1 and filling factor 2 showed exactly the same cross-under reflection, strong cross-under reflection for certain fraction, and a temperature dependence that suggests parafermions. And right now, what we are trying to do is basically to tunnel into this parafermion state and try to see this zero bias peak. And we are also trying some other stuff, but for another talk. And I'll just finish with this and thanking the people I work with. Okay, thank you.
All right, thank you. Thank you very much, Yuval, for a great, clear talk. Is there any question? Herman, you want to?
Yeah, thank you very much for this nice idea and also great data. I have a question. You said that you should be of the size of the coherence length. But if I understand well, niobium nitride has a pretty small coherence length, right? Is this influencing in some way your results?
So the superconductor itself is around 80 nanometer width, and I agree. Like the coherence length of niobium nitride, right, should be lower, should be 40 or 50 nanometer. But I didn't mention it actually here. But the cross-under reflection that we see is around 1%. So that actually makes sense because you don't see 100% cross-under reflection, but you see a relatively small cross-under reflection, which would come exactly for this exponent coming down because of the width of the finger.
Did you try to use aluminum or something else?
So so the only thing you basically need a superconductor which can sustain a high magnetic field, right? So niobium nitride is kind of, you can use niobium titanium, but all of them are like niobium based. You see, even molybdenum rhenium actually doesn't have enough magnetic field.
Thank you.
No problem.
Dimitri, you want to?
One short question. For Andreev reflection, you should basically align the Fermi level of your conductor to the gap of your superconductor. How this condition is ensured in your device?
So the superconductor itself is grounded. So we should think like the Fermi level, when my contact at the ground state, the gap of the superconductor is around the Fermi level. And now I apply a current into, or a voltage, doesn't matter, to the quantum Hall edge, and basically then I'm impinging in a higher energy. You see what I mean?
Yeah. But
Okay.
your quantum Hall edge only exists because you have a very strong depletion at edges, right? The band depletion. If you wouldn't have any band depletion, you wouldn't have any edge.
Mm-hmm.
Okay, so how this band depletion that you need to create the edge, how it holds near the superconductor?
So the super, you mean in terms of the feeling around the superconductor? That's
yes.
the.
Yes.
Okay, so I think this is a very very interesting question. I didn't touch it. I don't know if that's exactly what you meant, but the superconductor itself also dopes. Okay, so you can think that the density around the superconductor is actually at a higher density. So the picture is a bit more evolved than what I'm describing here. I can maybe, I don't know how much time I have, but I can annotate. For example, you could have other edge state which are propagating here counterclockwise. But in the end, what's actually important, and this is, I think, the essential part, when this electron impinges on the superconductor, there is only one way that it can go. Okay, it can only go in this direction, and all the doping region is basically counter-propagating to this electron flow. Okay.
Okay.
So Dimitri, I don't know if I answered your question, but
okay, don't worry. I think that we just should draw the band structure of your two-dimensional electron gas with conductance band, valence band, and connect it to your superconductor, and to see how they connect. You understand?
Yeah, I see.
And this connection, you will see that it will not be the same as connecting the same two-dimensional electron gas to vacuum, because your edge state is due to the connection of your two-dimensional electron gas with all bands to vacuum. This is the edge state. Okay. Now your edge state doesn't exist anymore, because instead of having vacuum, you have a superconductor. So my question is more related how these bands of that form your two-dimensional electron gas connect to superconductor, and then on a very smaller scale, how do they connect to the gap of superconductor?
Yeah, I understand. I think I see Yoni is having tension.
Maybe we leave this for the coffee break.
Yeah, sounds good.
Okay, thank you very much. In any case, thank you very much.
No problem.
All right. Thank you, Yuval. Okay, great. Sorry.